Hello, everyone. Today I'm here to present our work on the PolyScope framework. So first, the motivations. Android is currently the number one mobile operating system in the world. Due to its open source nature, there are many different OEMs with different implementations. In terms of the access control in Android, there are many major changes throughout the years. In the early days, Android relies on Linux stack and gradually added SEANroid support in Android 4.0 and made mandatory access control MAC fully enforced in Android 5.0. Other forms of defense like SEANroid multi-layer security and scope storage are later added into Android. So what can go wrong? With AOSP changing rapidly and its complex access control model, it's hard for OEMs to keep up with the changes. Also, OEMs change access control policy extensively for new functionality and to add value to its devices. This could cause policy misconfiguration and eventually lead to vulnerability. So here we give an example of a vulnerability. At first, the adversary has no access to the target file. Then it planted the symlink to in a directory that it has write access to. Then adversary sends a malicious intent to a vulnerable component, which accesses the symlink file and resolve the symlink file to the target file, which lead to an unwanted modification of the target file. We call this a link traversal attack. So we ask, why does such attack happen? So first, it's because access control allows adversary to create symlink in a directory that victim has access to. And second, victim resolve the path name without proper sanitization. And we ask the question, can we automatically detect such kind of vulnerability? It is very hard because one, there are a lot of data flows and we don't know which ones to test. And we don't know, and the second is we don't have a systematic way to separate trustworthy subjects from untrusted ones. So what can we do? We should first triage information flows and identify only the risky ones, and convert risky flows into test cases for attack operations. So the first limitation is that we have too many data flow. And what we do here is identify meaningful adversaries for each subject, and only flows that adversaries can impact are relevant. We refer to such risky flow that adversaries can impact as integrity violations, so IVs in this case, which refers to a case where adversary can modify a resources that may be used by potential victim subject. In this example, adversary subject B is authorized to perform write-like operation on object O, and victim subject A is authorized to perform read-like operation on object O. And in this case, we say object O's use by subject A is an integrity violation for subject A. The two other limitations we face is policy flexibility and unexploitable flows. So there are some access control policies like DAC and Android permission, which are mutable. So if we don't address the possible flexibility, we might miss some attack vectors. Next is Android configuration may block exploitations. This includes system configuration and other ad hoc defense techniques. This will make some IVs unexploitable, and we should remove those from testing. So the goal of PolyScope is to identify these risky data flows in terms of attack operation to greatly reduce the effort needed for runtime testing. PolyScope solves key problems by one, identifying per program adversaries, two, accounts policy flexibility, and three, further triage IV into attack operations that may be used in attacks. So previously, researchers identified possible adversary for a subject by either guess at trusted subjects or guess at adversary, which are both very ad hoc and one-dimensional. So in this example, in terms of system server, it is obvious that third-party application is untrusted, but should Bluetooth service, which is a system service, be trusted, or should OEM apps be trusted in this case? In PolyScope's trust model, we consider both worst-case trust and best-case trust. Where worst-case trust is a subject must trust other subjects that can trivially compromise it. And best-case trust, we constructed based on Google's process privilege level. Under our definition, we expect worst-case trust must be a subset of best-case trust. Otherwise, privilege level definition are missing fundamental trust requirement to prevent trivially compromising a subject. We are able to verify that both Google and OEM's policy complies with our assumptions. Mostly based on Android's functionality and design, here are the process privilege levels, where T5 is the most privileged and T0 is the least privileged. Next, we need to consider the policy flexibility. So the first type of permission expansion is adversary expansion. So in this example, adversary subject A, as shown, has the DAC and MAC permission at this point, and then it requests a Bluetooth permission, and after granted, we see that the adversary gains an extra DAC supplementary group, which is netBT, which give it extra permission. And we call this adversary expansion. The next type of permission expansion is victim expansion, where we see adversary may delegate DAC permission to objects that they own to victims. In most cases in Android, victim has MAC permission to the adversary own objects, but DAC permission will block victim from accessing such file. So in this case, adversary can do a chmod and then grant victim access to the files and create new integrity violations. So to account for permission flexibility, for adversary expansion, we assume user will grant all non-signature Android permission to applications and assume the whitelisted apps, so OEM apps, platform apps, may obtain signature level Android permissions. In terms of victim expansion, we expect adversary, when given the chance, will always delegate permission to victims. But this can only happen when adversary owns the corresponding object. So PolyScope identified 3 types of integrity violations. For more detail, please refer to our paper. So next, we address the problem where IV isn't exploitable. For example, in case of a link traversal attack, adversary must be able to plant a symlink file. However, some Android file systems do not allow symbolic links, so it is impossible to perform such link traversal attack. And some other Java level defense like file provider clause will also stop link traversal attack from happening. So we need to remove such IV. So the IV does not transform into a link traversal attack operation. Next, we discuss the key evaluation from our paper. So the first question we ask is, did defining per subject TCB make a difference? And the answer to that is yes. Computing integrity violations instead of data flow results in much better runtime and less data flow to test. Actually, a lot less. And the next question is, did permission expansion increase the attack surface? And the answer to that is also yes. By considering access control policy flexibility, IV's number actually increased from 122% to 1,550%. And the next question is, does the PolyScope reduce attack operations from IVs? And the answer to that is also yes. By taking Java level defense and file system configuration into concern, where we found that 14 to 21% of the IVs failed to be realized as even a single attack operation. We also highlight that OEM customization on access control policy really make things worse and should be systematically tested with tools like PolyScope to identify policy misconfigurations. Next, we go over a vulnerability we found with PolyScope. So in this attack, Attacker first gained a DAC group ID log through Android permission, which is a case of an adversary expansion. And then adversary replaced the part of reset_reason.txt file with a symlink targeted to a file in encrypted file system. And the subject reset_reason became victim of a confused deputy attack when attempting to record reboot logs. It ended up being the reset_reason subject is writing into the encrypted file system and could possibly break a device. This vulnerability is assigned a CVE number, but and it has been patched before our release. Next, we highlight the performance improvement through parallelization for PolyScope. We can see a significant improvement in runtime. And we would like to also point out that defining finer per program TCB really reduced the runtime needed comparing to computing information flows. To sum up, we developed a novel analysis approach to generate attack operations from a combination of access control policies. And we're the first work to include flexibility of access control into the analysis framework. And we apply PolyScope to multiple Google and OEM Android releases, discovering 2 vulnerabilities. So our biggest limitation at this point is that an attack operation is not necessarily a vulnerability. We need to confirm that victim does use the risky object through manual testing to confirm vulnerability. So in the near future, we hope to automate this process and are finally able to detect vulnerability automatically. That concludes my talk, and now I will take questions.